Welcome to this lecture on Pediculus humanus, commonly known as the human louse. Have you ever wondered why a simple, itchy scalp can lead to a school-wide letter sent home? Today, we are going to explore the fascinating, albeit slightly unsettling, world of these tiny hitchhikers. We will uncover their biology, understand why they are so medically significant, and even use mathematical modeling to see exactly how a minor infestation can explode into a major public health crisis. Let us dive in. To begin our journey, we must first understand what exactly this creature is. Pediculus humanus is a highly specialized blood-sucking insect that has evolved alongside humans for thousands of years. It is classified as an obligate ectoparasite. The word obligate is key here. It means this insect absolutely cannot survive without feeding on human blood, and ectoparasite means it lives on the outside of our bodies. Morphologically, they are perfectly adapted for their environment. They are small, wingless, and have flattened bodies that allow them to navigate close to the skin. Furthermore, their legs end in specialized hook-like claws, which are perfectly designed to tightly grip human hair or the fibers of our clothing, making them incredibly difficult to dislodge. Now that we know what a louse is, we need to distinguish between its two primary forms. There are two distinct subspecies of Pediculus humanus that you must know for parasitology. The first is Pediculus humanus capitis, commonly known as the head louse. This is the variant that causes intense itching on the scalp and is frequently found in school-aged children. The second subspecies is Pediculus humanus, which is the body louse. Unlike the head louse, the body louse prefers to make its cozy home in the seams of clothing rather than in human hair. While they look very similar under a microscope, their choice of habitat on the human host leads to vastly different medical consequences, which we will explore next. Before we discuss the diseases they carry, let us look at how they grow. What you are seeing here is the three-stage life cycle of Pediculus humanus. Starting on the top left, we have the egg, which is commonly called a nit. The female louse firmly glues this nit to a hair shaft or clothing fiber. After about 6 to 9 days, the nit hatches into a nymph, seen at the bottom. The nymph is essentially a miniature, immature version of the adult. Over the next 7 days, the nit feeds on blood and molts until it becomes the fully mature adult louse, shown on the right. This rapid development cycle is exactly why infestations can take hold so quickly. Understanding their life cycle brings us to a critical question. Why do we study them so rigorously? You might assume they are just a minor nuisance. While head lice are mostly just irritating, the body louse is a highly dangerous vector for several severe human diseases. Historically, body lice have transmitted epidemic typhus, trench fever, and louse-borne relapsing fever. These diseases have literally wiped out massive armies and devastated populations during times of war and famine. Even today, body lice outbreaks are a critical public health indicator. They frequently emerge in refugee camps, homeless populations, or anywhere that severe overcrowding and poor hygiene exist. Preventing these deadly outbreaks requires us to understand exactly how fast they can multiply. This historical danger leads us directly into the population dynamics of the louse. To truly appreciate why a lice infestation can spiral out of control so quickly, we have to look at their reproduction. A single female louse can lay up to 6 eggs per day. Because their food supply, human blood, is readily available, there are no immediate environmental restrictions on their growth. This means a very small initial population can explode into a massive infestation in just a few weeks. To combat this, Epidemiologists and doctors rely on mathematical modeling. By using mathematics, we can predict the exact severity of an infestation over time if no medical treatment is applied, allowing public health officials to intervene before diseases like typhus can spread. Now that we understand the need for modeling, let us look at the specific mathematical tool we use. This is the standard exponential population growth equation. It comes from the biological reality that the lice reproduce continuously at a rate proportional to their current population. Let us break down the symbols. N of t represents the total number of lice present on the host at a specific time t, measured in days. N0 is the initial population of lice that first colonized the host. The constant e is the base of the natural logarithm, fundamental to continuous growth. Finally, R is the intrinsic growth rate per day, which depends on factors like temperature and egg-laying capacity. If the initial population or the growth rate increases, the final population will explode much faster. Before we move on, let us see this formula in action with a concrete example. Imagine a child returns from summer camp with an initial population of just 5 adult female lice. The estimated continuous growth rate is 0.15 per day. We want to know how many lice will be on the child's head after 20 days if left untreated. We start by substituting our known values into the exponential growth model. The exponent becomes 0.15 times 20, which simplifies neatly to 3. Evaluating e to the power of 3 gives us a growth multiplier of approximately 20.085. Finally, we multiply this factor by our starting population of 5, yielding 100.425. Since we cannot have a fraction of an insect, we round this to 100 lice. In just 20 days, 5 lice have multiplied into a severe infestation of 100 parasites. This rapid multiplication we just calculated leads us to an important clinical application. In public health, medical guidelines often define specific population thresholds where the risk of disease transmission becomes critical. For instance, a population of 500 body lice on a single host poses a severe risk for transmitting epidemic typhus. As epidemiologists, we do not just want to know how many lice there are after a certain time, we need to know exactly how many days we have until that dangerous threshold of 500 is reached. To find this, we have to work our exponential equation backward. We must isolate the time variable, which is currently trapped up in the exponent. To do this, we will rely on a standard algebraic technique using natural logarithms. Let us apply this logarithmic strategy to a real-world scenario in a refugee camp. A patient is exposed to 10 body lice with a growth rate of 0.12 per day. We need to find the time it takes to reach the critical threshold of 500 lice. We set up our equation with 500 on the left and our growth expression on the right. First, we divide both sides by 10, showing that the population must grow by a factor of 50. Next, we apply the natural logarithm to both sides. The natural log of 50 is about 3.912, and on the right side, the natural log cancels out the base e, bringing our exponent down to the baseline. We now have a simple linear equation. Dividing 3.912 by 0.12 gives us 32.6. Clinically, we interpret this as approximately 33 days until the patient is in severe danger. So, we have calculated that it takes 33 days to reach the danger zone. This brings us to the real-world meaning of our math. This 33-day time frame is not just a number on a page. It represents a critical intervention window for public health officials. It tells doctors and epidemiologists that they have roughly 1 month to intervene with hygiene measures, chemical treatments, and pediculicides. If they fail to act within this specific time frame, the risk of a deadly typhus outbreak becomes critically high. This perfectly illustrates how abstract mathematical modeling directly informs and guides real-world medical and epidemiological decisions, ultimately saving lives in vulnerable communities. We have covered a lot of ground today, so let us review the key takeaways. First, Pediculus humanus is a highly specialized, blood-feeding ectoparasite that relies entirely on humans for survival. Second, while head lice are a nuisance, the body louse is a dangerous vector capable of transmitting deadly diseases like epidemic typhus. Third, because these parasites reproduce continuously, even a minor infestation can escalate exponentially into a severe medical issue within weeks. Finally, we saw how mathematical modeling is absolutely critical for predicting these outbreaks, allowing us to determine exact intervention windows. Understanding both the biology and the mathematics of the human louse is essential for effective public health prevention. Thank you for joining this lecture.